All right, so this is Math 409 problem solving. This is our last meeting before the Putnam. And so we just saw a proof that the integral log of 1 plus x over x is pi squared over 12 if we know the sum of 1 over n squared is pi squared over 6. But we want to now use that information to evaluate the second part. So what's the first thing you should do when you have a double integral like this? Wait, maybe, did we do this?
Yeah, I thought we did this question.
Yeah, oh no, I think we did do this because we drew the picture. Right. And it's, when you see something like this, it's always, this is going to be a Fubini. Okay, so we have done that. Okay. So were there other problems from this that people wanted to look at? And we also had, I think, I don't know if we did all the problems from earlier. These are the same ones. Same ones. We did the binary star. So let's see, yeah. I think we might have done all the ones here. Yes. Okay. So other ones we have here is we have problem 9 star. I think we did 4 and 11. We haven't done 8. We haven't done 2. Were there any problems that people found particularly interesting? 2? Okay. So what's the first thing you should do when you see a problem like this? The BB and A by B by C brick. C1 is the set of all points that are at most 1. Draw a diagram. All right. So C is the set of all points whose distance from the brick is at most 1. So I will choose red for my brick. I'm a traditionalist. So here's the brick. And now we want to look at all points that are within 1 unit from it. So I think there are going to be certain regions that are going to be easier to study than others. So we'll have, say, A, B, and C. And we want to be within 1 unit. So I think coming down is going to just be another similar brick, but just 1 unit, right? So, and then you'll have 1 above. I'm sorry? Oh, is there a typo? I think it's a typo, yeah. I think the brick is B, and then I think C equals C1. So it might be, better notation might be C R is the set of all points that are R units from the brick, and they want to find C1. That's what I think, and they're just going to call that C, but I think they want all points that are within 1 unit of the brick. So if you draw this, there are certain regions that should be pretty easy to come down. You go straight down 1 unit, and you have the top as well. Then you have the sides, and you have the caps. So what does that give us? So we have 6 nice regions. What will those be? Right, so what would be the volume of that thing down there? AB, and we would have it twice. And then we would have AC twice, and we would have BC twice. So we know the 6 nice regions give 2 AB plus AC plus BC. And now we have to figure out, what's going on in the other parts. It's coming out as well. So some of them I think are going to be pretty easy to figure out. When you have part of it coming out and part of it coming down, what kind of shape are you going to have in between?
Quarter cylinders.
Quarter cylinders. So we would have 4 quarter cylinders going around like that, right? So 4 quarter cylinders. But right, well, I'm saying for the ones I'm doing this way, yes. Then we would have the other direction. So if we're going in this direction, horribly drawn, for the quarter cylinders, what are their dimensions going to be? The length is A. The radius is 1. So length is A, radius is 1. And does C come into play at all? And does B come into play at all for these? No, right? So this gives, so if we take them, we can just put them together, make a full cylinder, so the 4 goes away. The base is going to be pi times 1 squared, and the height is going to be A, so it should be pi A 1 squared. Just put in a few details as to how you're getting this. Okay, so that's going to give 4 more pieces. Then we should have similarly for B, similarly for C. And none of these are going to be double counted, right? Similar for other 2, giving pi B 1 squared plus pi C 1 squared. Are we missing anything?
The corners are each like 1/8 square.
So we should have spheres coming into place now.
Yeah, but it will like combine into 1 sphere.
And it should combine into 1 sphere, right? So that we now have something coming down here as a cylinder, something going over there like a cylinder, and then there's that little corner down there. Think of it almost like a Rubik's Cube, where we've got the center, and then we've expanded to the centers of each of the 6 faces. Then we've got the 12 pieces that are coming in next, and now we have the final 8. And so now we have 8 quarter spheres, right? But if we have 8, is each one of them is 1/8 of a sphere, right?
Yeah.
Right. So we get 1 whole sphere. So yields 1 sphere. And what's the only thing that the radius could possibly be? 1. And so what is the volume of a sphere? 4/3 pi 1 squared. So I think that's all we need to do for this problem. So yeah, we need to add all these together. That's a good question. Yes, you would have to add the brick. Good catch. Oh, sorry, yes.
Is there some systematic way we can use the check if we counted all the raw ingredients, or is it just all kind of visual?
I think it's just draw as good of a picture as you can, and just make sure that you don't double count everything, and just go through it very methodically. Make sure you hit it, you hit it, you hit it, you hit it, and then, as was remarked, make sure you answer the question that was asked. And so the question that was asked is, it's all points in R3 that the distance from P to C is at most 1. So if you're inside the brick, your distance is 0, and those should be counted. And so I don't know how they would give points. I would say if you did everything but forgot to include the brick, that should hopefully be worth an 8. Is that you clearly know how to find the volume of a brick if you've just done the cylinders and the spheres.
Wait, can you just explain again, like, without thinking about it visually, why it's 8 spheres?
Sure, I can try.
Yeah, I thought about it as 4 quarter spheres rather than 8 white spheres.
So if you think of a Rubik's cube, it's like this. And I probably should have, started off better. Red. This will be yellow.
Which is on the right?
Yes, okay, that's what I thought. So if you look at this cube, there's 27 pieces in the cube. We start off with the brick, which is in the grand center, right? And so we can't see that because we're going to cover it. So the center, the brick, we can't see. The first thing we do is we put out things going 1 unit in each direction. That's going to give us in step 1 this red piece over here, this blue piece over here, this yellow piece over here. So that's the very first step. The next step is we put in these cylinders. And so step 2, you would be this cylinder over here, this cylinder down here, this cylinder here, this cylinder here. And that's the same as coming from that cylinder over there. Oh, I should have called these, sorry. And then this was a 1. And so this is the second step, is putting in the 2s over here. And now we need to figure out how do we fill in the stuff. And that's going to be, I'll just save time and just do like a 3 for the corners. Something like that. So I hope that helps you somewhat visualize. So we have some nice formulas. So the volume is 4/3 pi r cubed. Surface area is 4 pi r squared. For circle, the area is pi r squared, and the perimeter is 2 pi r. And what you notice is we take the derivative. So if you think about what's going on, I'll do the circle case. So I give you a circle of radius r, and I increase r, not even close to drawing by scale, by delta r. So what's the change in area? So what would be the change in area?
Pi of
So what's the change in area? Well, give me the subtraction problem to find the change in area.
pi delta r plus r squared.
Good. Pi. Normally we do r plus delta r squared minus pi r squared over delta r. The pi r squareds will cancel. We'll get a 2 pi r delta r over delta r, which cancels, plus a pi delta r. And as you take the limit as delta r gets smaller and smaller and smaller, what do you think delta a over delta r is going to? Yeah. this is giving us, this quantity in here. So as delta is getting smaller and smaller and smaller, what should be a decent approximation for the area of that ring? Why?
Because as delta R gets closer to 0, but that second term tends to 0.
Good. So this would go to 0. So if we just calculate this limit, we get 2 pi r. How else can we think about what we're doing? How else could we try to estimate this area? Yeah, maybe approximated by the perimeter times the thickness. As that might not be a bad approximation. Maybe this should be approximately the perimeter at R times delta R. And if that's true, then the limit as delta R is going to go to 0. If that's the area, the change in area, then the change in area over the change in R should go to the perimeter. And you can do something similar for a sphere. The shapes fit very nicely. And so if you forget one of the formulas, as long as you remember something else, you're okay. Okay. Any other problems here that looked interesting? We still have a little bit of time.
Oh, sorry, 9 again.
Which one?
9.
Where is 9?
Top right.
Oh, there's 9. Okay. So let n be a positive integer, and fn is the last non-zero digit in the decimal expansion. So f5 of n factorial. Okay. So if we look at like a little table, here's n factorial, here's f of n. So 1, 2, 3, 4. I was debating just going and pasting this because we made a table of factorials last time. So it's 1, 2, 6, 24, 120, 720. And so fn would be 1. Am I doing this right?
Yeah.
Okay. Okay. 1, so 2, then it would be 6, then it would be 2, then it would be 1, then it would be 7.
Fourth should be 4.
I'm sorry?
Fourth should be. Oh, yeah.
Oh, okay, good. Okay, good. No, I got confused and I thought they meant the furthest to the left. They do mean furthest to the right.
Oh,
I was reading 4 as 5. And it said F5 was 2, so I thought, oh, okay, maybe they're doing the first digit. Okay, this is better. Good. So this is 4, then this will be 2, and then this will be 2 again. Okay, and so what they want us to do is to show that if A1, A2, AK are distinct positive integers, then f of this quantity depends only on the sum of the a's. Okay, so show if, let's say A1 strict 0 less than A1 less than A2 less than ... less than AK. We might as well assume that we're writing them in increasing order because this symmetry, that f of 5 to the A1 plus ... plus 5 to the AK depends only on A1 plus AK. Can we get much data on this?
because the numbers get very large very soon.
The numbers get very large very quickly. We're not going to gather much data. So that tells us that we have to be able to attack this without gathering too much data. Now we only care about the furthest digit to the right, the last digit to the right. So when I look at numbers, when I look at n factorial, what really matters when I'm looking at a number like n factorial in terms of the products? And I only care about things that will affect the first non-zero digit. So if I needed to calculate, say 12 factorial, how much would I have to really work with?
Put around as many tens as you can and then take one ten.
Well, I'm saying, do I only care about the ones digit? In the product for n factorial. If I give you 27 as a factor, can the 2 change the ones digit? Is that possible? What do you think? So we're calculating, say, n factorial. Say we have, I'm thinking 3x plus 1, so 27 is on my mind. So I'm looking at 27 factorial. And this is going to be, a long nightmare, something, and then a bunch of zeros. And now when 28 comes in, when I'm multiplying, if I have something that's non-zero, when I multiply it by something that's non-zero, it's still going to be not zero.
Oh, I see.
Right? So when I'm doing the multiplication, if I only care about the last digit that's 0, this doesn't matter. Right? And so now, if 28 comes in, really, I could write this as 20 plus 8 times all of this. And the 20 is not going to affect the last digit. And so it's going to give me a new mess, a new star, and then a bunch of zeros. So I think when we're doing the multiplications, we only really worry about the last digit. That's still going to be a little bit painful. 7, 8, 9, these become large numbers. But as we're going through, when we're constructing our table, 1, 2, 6, 24, do I really need to keep the 2 in the 24? Right? So could we actually make a new modified table? So we'll have n. We can't use shop because shop actually means primorial. So I'll use the @ sign and then f of n factorial. So now if we go 1, 2, 3, 4, 5, 6, 7, 8, it would be 1, 2, 6, 24. We can just do that as a 4. We multiply by 5, we get 20. Right? Multiply by 6, we get 2. Multiply by 7, we get 4. Multiply by 8, 2 again. And so I should have left a little bit more room to do 9 and 10. So when we have 9, what would we get with 9? We'd get 8. And then when we have 10, we would get 8. And now when we have 11, we would get 8, 12, 16, so it just become 2, 13.
Oh, it's 6.
Oh, sorry, 6. sorry. And then 13 would be 6 and 3 is 18, right? So we can actually start generating the sequence. Is the sequence going to be periodic? So possibly is absolutely a correct answer, right? There's no way to dispute possibly being correct. Hopefully, that's also, you're welcome to hope. Well, what do we know about the ones digit of all these numbers but one? They're even. And so the question is, does it have to eventually cycle? Could we have longer and longer patterns before it cycles back? If we have a certain finite length, we know eventually it's going to have to repeat. So here's one of my favorite problems. So let's look at the Fibonacci numbers. So 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, ... We can look at the Fibonacci numbers mod 10. And so if we look at the mod 10, we get 1, 1, 2, 3, 5, 8, 3, 1, 4, 5, 9, 4, ... Do we think eventually, if we look mod 10, that the Fibonacci numbers will repeat? Why? There's only finitely many pairs. Eventually, we're going to have to get the same two numbers consecutive with the last one's digit. And then from that point onward, it should be the same argument we've done before. It's easier if we look at it mod 2. The pattern's faster. Then it's going to be 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0. Much faster to see the pattern, hitting when we're looking at things mod 2. But if I look at mod p, there's p squared possibilities for pairs. And so if I look at, say, p squared plus 1 numbers consecutive in a row, what can we use? Pigeonhole principle, right? And so by the pigeonhole principle, eventually there will have to be a repeat. And once you have two parts in the sequence that are the same, well, from this point onward, what happens? It's now the same as this. That's going to be the same as that. It's now going to be cyclic. So we know as soon as there's a repeat that it becomes cyclic. So the question is over here, does it have to eventually repeat? And how far do we have to go before we'll eventually repeat? What do you think?
Yes, because you always multiplying two numbers and the two numbers have one options.
Right, and so the issue is going to be the fact that we start with the numbers 1 through 9 in the beginning. We start off with that 1 that's an odd one in the beginning. So that could be a little bit problematic. Yeah, exactly. So, screw that. From that point onward, I think things are going to be good. And so we know every time we go through, a set of 10 numbers, it doesn't really matter what the tens digit, hundreds digits, whatever. All that matters is the ones digits of the numbers we're multiplying by. How many different possibilities can we have to start with? Well, we could start with the even number 2, 4, 6, or 8 was, right? So 2, 4, 6, 8 are the possible starts. We're screwing the 1. So we start with 2, and then we could have 10 numbers. And then if we got 2 again, great, we know we're done. Now let's say we got a 6. All right, we do another 10 numbers. We got a 2, we're done. We get a 6, we're done. We got an 8, damn it. All right, do it. Then we got a 4, damn it. but now we have to get either a 2, 4, 6, or 8, and now it's going to repeat. So how far do you have to go before it repeats? Worst case. Roughly, approximately. Will repeat in approximately how many steps? I don't think it's as bad as 100. I think it's 40. Because we have to start with a 2, 4, 6, or 8, and then let's say we do 10 steps and we get to a 6, and then we do 10 steps and we get to an 8, and then we do 10 steps and we get to a 4. And then we, at this point, if we get to a 6 or an 8 or a 2, it doesn't matter. We've now repeated. And now we're going to be doing the same thing again and again and again. So in at most 40 steps, it's going to repeat. Have we done anything that is directly solving the problem? No. You know, right now we're basically just throwing some math and just trying to get a feel for what do we know about this problem. And so don't be worried about, you know, oh my God, I've got to solve this problem directly. You know, let me just play with it a little bit. Let me get a sense of what's out there. Let me try to see any patterns. Let me try to see some facts that might be useful. And so I want to just understand this function. How do I understand a function? I build tables. Well, you know, I don't have my calculator, which is good because if you had your calculator, you might actually be tempted to multiply these numbers out. And you know, since you don't have the calculator, you have to be able to do it without doing those painful multiplications. Okay, so now we eventually figure out anything to the left of the digit doesn't matter, the first non-zero digit. So we might as well just constantly reduce these. And then as we're multiplying by other numbers, all that really matters is the ones digit. And now we get very quickly to it's got to be periodic. It's going to be at worst a period of 40. And so now, how is this related to? It depends only on the sum. So let's do it n and then f of n. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and then n. So I'm wondering if the period's related to some multiple 5. 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. And so yeah, the question is, what's a good number to be looking at? It could be maybe looking at it where it is 5. So let's start putting in the numbers. So it's 1, 2, 6, 4, and 2, right? And then the next set is going to be 2, 4, 2, 8, 8. And then it's going to be 8, 6, 8. 9 times 8 is 72, and 1. Oh, so wait, 1 is a possibility.
Ah, interesting.
Okay, 1 is a possibility, so we made a mistake. So how long could the period be? Well, wait, if 1 is a possibility, depending on what comes next, could we have 3, 5, 7 coming in as well? Or is 1 the only possibility?
Like 1 could only come after 5, or
Because you always end up look at 5.
So I think we might only have to fix this by allowing a 1. Okay, so the only trouble is going to be if we have a 5, which could give us a 1. Okay, that might be good in terms of all the 5s that are coming in. All right, so now after the 1, we have 6. So that's going to be 6. Oops. So it's going to be 6. 7 times 6 is 42, right? 8 times 2 is 16. 9 times 6 is 54. 8. Yes. And then multiplied by 1, so we're going to get 8, 16. Did I make a mistake? Or are we repeating at this point?
Yes.
All right, then 6 times 3 is 18. 8 times 4 is 32. And 5 times 2 is 1. So 8, 6, 8, 2, 1 with a 15. Good. And then these are going to all be the same. So we've now got a repeat. Okay, so where do we say the repeat starts? So 11 with the 8, and then the 21. Are those what we're going to say is the same for the repeating? Okay. So all that really matters is what is your number mod 10? Yeah, as long as your number is at least 11, I think all that matters maybe is what is your number mod 10 is just what is the ones digit. So just need your number mod 10. And so now if we, I lost the copy, but so now if we look at this, hopefully what this means is that the value of 5a1 plus 5ak, if we only care about what that is mod 10, that should just be related to the sum of the exponents. So that's now, it's 10:50, it's time to stop, but that's, I think, how you would finish this problem, is that we've now reduced it to, we only need to know what is our number mod 10, and if I have something like this to figure out what is this number mod 10, well, I only need to know what the ones digits are of your 5 to the 8.
So is that how they expect you to solve this problem?
I don't know.
Replacing it?
I don't know. Again, you can look up Putnam's and see what they suggest for the way to solve this. I don't think this is a terribly bad way to solve this problem. Sometimes what happens is once you solve it, then you look backwards and you now say that I can reduce it without doing all the calculations that I've done. Now that we saw this with what Jack presented, is once I saw his, well, we could just rework it this way. All right. So I will stop recording here.